Okay, so good afternoon, everyone, and welcome back to this third session of the training with neutral atoms, quantum computers by Pasqal. Uh, Let me start by sharing my screen. Can you see my screen okay?
Yes, we can see your screen.
Perfect. So for today's lecture, the plan is to talk a little bit more about optimization type problems, in particular optimization with graphs. And for that, I'm going to start by introducing the concepts about what graphs are, for those of you who are less familiar with this mathematical object. Then we will go through a set of combinatorial optimization problems and the types of problems that people typically look at when they tackle implementations, especially early on implementations with quantum computers. Then we will discuss how these implementations can be carried out by neutral atom systems. So we will refer to a little bit of what we have done in the previous session on Wednesday with Pulsar Studio. So I'm going to show you once again the tool, and we will look at one of the main examples we discussed, but purely from an optimization perspective instead of a quantum simulation perspective. And we will end today's session by a deep dive into a particular type of problem that's called the maximum independent set problem, which will serve as, I would say, as an introductory example on what kind of problems can be solved with particular efficiency, and what is the potential impact of solving these types of problems with a quantum computer. So let's start with a little bit of an introduction. So for that, the first thing we need to discuss is what graphs are. Or graphs in mathematics are one of the fundamental objects that serve as a foundation for many combinatorial problems. They have been rigorously introduced more than 200 years ago by a German mathematician who was interested in studying from a theoretical perspective, especially routing type problems. So graphs are nothing else but a collection of nodes, points that are called vertices, and a collection of links or connections between these nodes or vertices that are called edges. So here in the image, you can see a very, very simple example of a graph. As you can see, for it to become a graph, mathematically speaking, we only need to define nodes and edges drawn in between certain nodes. So not all nodes need to be connected. Nodes can be connected with no other nodes as well. In the basic scenario, there can only be one edge between two specific nodes. If we allow for multiple edges, then we are talking about a multigraph or a higher dimensional graph, depending on the interpretation. But we will focus on this more basic fundamental concept of graph. So graphs are all around us. They are present in various different settings. So I've taken the same illustration and represented it with two very different concepts. So as you can see, the same graph can arise as really an itinerary on a map. A collection of roads and intersections or points of interest in between. Or it can arise from a schematic representation of a particular object construction. Here in this case, it's a specific type of circuit. But we can find graphs in various walks of life. For next week's deep dive session, we will deal in particular with telecommunications based graphs, or that in that domain are called networks. I will illustrate a little bit how they arise in particular, but you can really find graphs in various different industries and domains nowadays, and not just from an industrial perspective, but also from an algorithmic perspective. So for those of you who are more well-versed, for instance, in machine learning, deep learning, or neural network architectures are nothing else but large realizations of graphs from an algorithmic point of view. So they are really all around us. Having a better understanding of these mathematical structures is key for us to be able to propose efficient algorithms to solve problems that can be defined on them, or make methods that rely on these structures much more efficient. So when we talk about graph combinatorics or optimization on graphs, we can refer to a whole plethora of different types of problems. So here I wanted to illustrate a couple of different problems that you can define on a graph. So what I've done is I've taken, just for as an example, the map of the United States of America, and I defined certain points of interest, which in this case are cities, and these cities are connected by roads. So in our graph representation, we have a collection of nodes that correspond to these towns, and edges, links are drawn between these nodes. Then we have sort of direct itinerary in a sense. And one of the, I would say, most famous combinatorial optimization problem on graphs is what we call the traveling salesman problem. Probably you have heard about this. So this is a problem that tasks you, the problem solver, in finding an itinerary, finding what we call a Hamiltonian circuit that goes around all the different cities, and going around all the different cities, reaching back to the initial departure town. In the basic scenario, this is an elementary decision problem because you just need to verify that you can reach each of the nodes and you can continue your moving from that node to the next one. However, what makes this problem difficult is the weighted graph version of it. So when we talk about graphs, we can associate different weights, different numbers or key metrics, not only to nodes, but to edges as well. So in this specific scenario, when we are taking the map of the United States of America, with the roads or certain roads being the edges between the selected towns, we can associate, for instance, traveling cost, distance, or any kind of other different metrics to each of the edges, to each of the roads present in the itinerary. And if you add these weights on top of the representation, then suddenly the problem becomes much more complicated, because the question you can ask is, how can I go around all the cities while, for instance, minimizing my cost, my travel cost, or minimizing the distance I am traveling in total? And suddenly it becomes a problem that's exponentially more complicated, because finding an efficient route would require you, in a sense, to test almost all potential scenarios. And the more cities you have, the exponentially more scenarios you can envision. So the problem can very quickly become very, very complicated. This is not the only type of graph combinatorics problem we can define. So here, in an unweighted, so without weights, without travel costs, this is a very simple search method, but we can look for much more complicated problems as well. So again, I'm taking the same graph. Now I've removed the map from the background for a more ease of read and visualization. And we can ask other types of questions about this graph structure. One of the other famous problems is called the max cut or maximum cut problem, which asks you to separate your nodes, in this case your cities, into two groups such that the edges that run between these two groups is the maximum possible. So basically what you would need to do is to put part of the nodes on the left-hand side, the other part of the nodes on the right-hand side, and you want to ensure that the number of edges that run in between the left and the right-hand side is the maximum possible in order to cut, in order to separate this. So this is a type of combinatorial optimization problem that arises a lot in logistics and supply chain management type problems typically. Another important problem that we are going to discuss a little bit more is what we call the maximum independent set problem. So this asks you to find a collection of nodes, a collection of vertices, such that no two of these vertices have an edge drawn between them. So when you have such a collection of nodes where there is no edge between any two of the selected nodes, it's called an independent set. And if you are able to find the maximum amount, so the maximal in a sense, we are going to discuss the definition in detail a bit later, that can provide some key features on the graph's structure. This key feature then can be used, for instance, to build a much more complex graph combinatorial problem. This problem is typically referred to as the vertex coloring problem. So in the vertex coloring problem, you are not selecting nodes, but you are associating colors or labels or indexes to each of the nodes, such that any two neighboring nodes cannot have the same color, they cannot have the same vertex. So this is, again, a very famous and historically present problem because this was introduced as part of a series of graph challenges back in the 1800s, wherein people were interested how to efficiently color maps. So coloring maps requires a similar strategy because on a map you have different countries, and ideally, for an ease of read, you want to color neighboring countries with different colors. And so this gives rise to a similar type of problem. And for that, mathematicians have found an efficient way to go about solving this problem. Moreover, they have also proved that any map, any two-dimensional map, can be colored by at most 4 colors. Here, for the vertex coloring, the situation can become a bit more complex depending on the structure that arises. But we will go into a little bit more into the detail on the second half of this lecture. For now, I just wanted to illustrate that graphs are really just a collection of nodes and edges, and there is a wide variety of types of problems that you can define on graph structures with various different implications. So with that said, let's move on to discuss a little bit more about combinatorial optimization problems. So now taking a step back from graphs and focusing on purely a mathematical representation of certain types of combinatorial optimization problems. Why we typically put forward these type of problems, especially when we are talking about quantum computing. The reason for this is that combinatorial optimization problems are typically considered very, very complex, very, very difficult to solve with classical computational devices. Next week, we are going to discuss a little bit more in detail what we mean by a difficult problem for a classical computer. There is a whole branch of mathematics called complexity theory that deals with defining exactly what is meant by a difficult problem or what's meant by an easy problem. So these are different problem classes that can be defined for classical computers as well as for quantum computers. A lot of the combinatorial optimization problems fall into the more difficult problem classes for classical computers. The reason for this is that typically the solution space scales exponentially with the number of variables, meaning that if you add one extra variable, the potential solutions, the solution candidates, multiply by a factor of 2, 3, 10, etc. Moreover, for these types of problems, there is not just the scale that needs to be considered, but the additional conditions, the additional constraints that can make it increasingly more difficult. Typically, for a combinatorial optimization problem, there is a set of variables, a set of entities on which we want to perform the optimization tasks by applying a cost function, so some kind of metric that needs to be optimal, be it maximum, minimum, or a combination of the two. And performing this optimization task can be under certain constraints, under certain limitations. So these are the three main components that go into an optimization problem, and then we are expected to find a good strategy that provides a good solution or ideally the best possible solution, whenever it's possible. We can find combinatorial optimization problems in various different fields. So here I've collected a couple of typical examples. Some of them are much more obvious, while others can be potentially quite surprising. Typically, resource management type problems fall into this category, be it from a logistics perspective or more generally a scheduling type problem. People are dealing with this on a day-to-day basis. Whenever you're looking at your agenda, trying to fit in a meeting, trying to plan meetings with other people is a very typical and day-to-day life example of simplified optimization task, but you can make the situation much more complicated. Financial industry, for instance, is dealing with a lot of optimization-based problems, especially for financial portfolio management type tasks. So when we are dealing with these combinatorial optimization problems, as I mentioned, they tend to fall into what we consider a difficult complexity classes or difficult problems for classical computers. However, what has been shown is that for quantum computers, depending on the problem, they can become much easier to solve. This is in relation with the inherent properties of how quantum information works. So we have seen it on Monday that the state space, so the quantum states themselves also scale exponentially. So the potential variety, the potential amount of information you can encode on quantum bits or qubits also scales in a similar fashion as the problem itself would. Moreover, due to entanglement and other quantum mechanical effects, you can envision solution strategies that are able to leverage these quantum mechanical properties to provide much more efficient solution methods. And this efficiency can manifest in various different ways. So efficiency can be measured by the speed, reaching a solution or a solution candidate much faster than a classical method. This is sort of a long-term objective because typically these type of methods that allow to accelerate require larger scale quantum computers to function efficiently. Efficiency can also be measured by the accuracy. So how close the solution is to the optimal one, which typically is a very important metric because it directly relates to how good your solution is. But it can also be measured by more abstract factors. So one of the more abstract factors that I want to mention, especially with combinatorial optimization problems, is the fact that due to the superposition properties, results from a quantum algorithm or a quantum component in an algorithm typically contain a set of solutions, a set of solution candidates. So there is an inherent parallelization involved, which allows you to get access to not only one potential solution, but many potential solutions in a sense at the same time. This can become important, especially in real-world applications of optimization problems, because in a lot of cases for optimization problems, there are hidden constraints, there are hidden tasks that need to be evaluated either before or after the optimization cycle. So the optimization problem doesn't live by itself. It is part of a workflow. It is part of a work cycle. So having access to multiple solution candidates can potentially enhance the whole work cycle without having an individual impact on the actual problem component. And this is one of the key points that can provide even early advantage for these type of problem considerations. With that said, when we are talking about combinatorial optimization problems, from a mathematical perspective, we can formulate them in various different ways. So I wanted to start off with the easiest potential problem to formulate, which is called a binary linear programming type problem. So it's a binary optimization problem because each of the variables are binary variables, meaning that they can only have 0 or 1 as a value. And it's a linear programming type optimization because the function to optimize is a linear function. So as you can see, the cost function, so what we want to minimize in this case is a linear combination between coefficients, so the c's with indexes, and the binary variables, so the x's with indexes. This can be something simple with 1 or 2 terms, but this can be something with many different terms. So again, it is linear because it's a linear combination of known factors and the unknown variables. And it's binary because the variables can only have 0 or 1 as a value. The difficulty from this comes from the constraint part. Again, this is here a linear constraint that can be written with a matrix representation as well. So it's a set of inequalities, if you wish, that compare a linear combination of the variables, so what's on the left in each row, with known limits or factors. So this is, in a sense, one of the simplest optimization problem we can establish that can be tackled with, that has some actual impact, typically as an algorithmic component for optimization problems. And depending on the structure of the constraint, can already become not trivial or not easy to solve. Moving on from the linear part of the next step of complication or complexification, I should say, is quadratic type problems. So here is to introduce a mathematical concept that probably a lot of you have already seen if you have dealt with optimization problems for quantum computing, which is a QUBO problem. So QUBO stands for a quadratic, unconstrained, binary optimization problem. So as the name implies, it is quadratic. So instead of the linear formulation beforehand, it's quadratic, meaning that in the cost function itself, you have second order terms, so quadratic terms, and the cost function here is defined by this f function. The first term has a multiplication of two variables and with known coefficients. So this is the quadratic term of it. It is, again, a binary problem, so that the variables themselves are either zeros or ones. And in a simplest scenario, it is considered to be unconstrained. So there are no extra constraints. There are no extra inequalities or equalities to be verified. So if you look at the cost function, the first element was the second order term, so the quadratic term. The second element was the linear term. So this was the initial cost function in the linear programming problem. And eventually you can also add a constant term in the cost function, but that only shifts the value. So it doesn't play any significant role in the optimization task at hand. Why we are typically talking about QUBO type problems or quadratic unconstrained binary optimization problems when it comes to quantum computing. The reason for this is that these QUBO type problems can be related to a specific type Hamiltonian formulation, what we call an Ising type Hamiltonian formulation. So an Ising type Hamiltonian formulation is a physical representation of a spin electron system in which there are two body terms acting on the system. So each of the two spins present have an interaction term in between them. And on top of that, there is an external field, an external force acting on the individual spins of the electrons themselves. So this can typically be represented by such a Hamiltonian, so such an operator in a sense, where the sigmas are in theory polymatrices. In actuality, they correspond to the spin representation of our electrons. We have second order terms, so the first element that incorporate interaction, and the second term which incorporate the interaction with the external field. And putting the two, so the cost function of the QUBO formulation and the Hamiltonian, the operator from an Ising type evolution together, as you can see, there are some very key similarities in between the second order terms and the quadratic form, as well as the external fields impact and the first order terms. So there is an almost immediate equivalence or correspondence, I should say, in between these two, which gives rise to an inherent connection between a purely mathematical formulation of an optimization problem and a physical representation of a quantum system, which can then give rise to quantum implementations of this particular problem type. When we are doing such an implementation, there are many different strategies that we can leverage from a quantum computing perspective. So here I wanted to mention two main algorithms that are typically employed. One of them is, I should start with the variational methods. The most well-known in this case is the QAOA, so quadratic unconstrained quantum approximate optimization algorithm, sorry. But there are more generic algorithms as well, such as the adiabatic method. We will discuss them in a little bit in more detail, how these methods work. These leverage different parts of this operator representation in order to efficiently find the solution state or the solution itself for the problem. In particular, we are going to focus in the adiabatic type computation. So an adiabatic evolution or adiabatic computation relies on a slow evolution of the quantum state from a known initial state to the target solution state. For now, I will stop there in the introduction for the types of problems that we can handle. Now, we are going to revisit a little bit the neutral atom system in order to start connecting the first section, so what we've seen on graphs, with the second section, what we have seen as an introduction for combinatorial optimization type problems. As a reminder, so we have talked about this on Wednesday, that when we are dealing with a neutral atoms type quantum processing unit, the heart of the computer contains what we call an atomic register. So a collection of atoms that are trapped inside the machine, inside the vacuum chamber, and that are ready to be manipulated by specific laser lights. As I mentioned on Wednesday, but we are going to discuss this once again, the atomic register, so this collection of trapped atoms, can be represented by a graph. So the equivalence is in the fact that nodes are associated to atoms, individual trapped atoms, and edges are drawn whenever there is a physical interaction that can take place between two trapped atoms. And once again, as a reminder, the physical interaction between the atoms is a van der Waals type dipole-dipole interaction that can take place up until a certain distance. So it's a distance-based physical interaction that allows the atoms to enter into an interaction, into an entangled state, potentially, given that they receive sufficient amount of energy. So what it looks like in practice, or what it can look like, is as such a graph representation on the right-hand side, wherein we have taken an image, a fluorescent image from the machine itself that highlights the nodes that have atoms trapped in it. And we have overlaid that by drawing the dotted lines to represent the edges, so the physical potential interactions in between the trapped atoms. The collection of these tools, FC as seen by the definition, gives rise to what we call a graph from a mathematical perspective. Why is it important? It's important to keep in mind this mathematical representation, because this immediately connects any kind of graph structure with an atomic register representation, so with a specific geometry. As I mentioned, graphs can arise as part of the problem formulation, which in turn allows for encoding the problem structure itself on the machine directly. It can also arise as a structure inside an algorithm, which allows you to encode part of the algorithm in potentially a much more efficient way. However, what you need to keep in mind, what's important to keep in mind is that there is a specific type of graph structure that can arise inside a neutral atoms type quantum system. As I mentioned, the edges, the connections are distance-based because they are drawn whenever there is an interaction possible between two atoms, which cannot happen outside the Rydberg blockade radius. So the types of graphs that can arise are are what we call unit disk graphs, so distance-based graphs in which you need to draw every edge that connects atoms or connects nodes that are physically close together, distance-wise, within a certain threshold. Obviously, not all graphs are unit disk graphs because a lot of the graphs are not represented in a Cartesian system, for a starter. More or less, moreover, not all graphs can be represented by a unit disk graph. There are certain graph structures, typically for very, very dense graph structures that cannot be redrawn or repositioned in such a sense that it gives rise to a unit disk graph structure. For this reason, there is a specific field of graph theory that can come and help out, which relies on what we call graph embeddings. So finding a new graph representation that's structurally similar to your original graph. So it has still the same main properties, but is of a different type altogether. And with these graph embedding structures, with this connection between different types of graphs, we can find an intermediary that allows you for representation with a specified quantum system, if you wish. So with that said, I wanted to revisit a little bit what we have seen on Wednesday from a neutral for Pulsar Studio, when we started looking at how you would go about implementing a neutral atom system. So let's look at once again the antiferrometric state experiment. So one of the examples present in the Pulsar Studio environment. So for that, I've already loaded up the system for your convenience. So once again, as a reminder, for Pulsar Studio, it's really a graphics user interface that's overlaid on top of our Pulsar programming environment to allow you to experiment and explore in a zero code or a no code fashion for, in particular, neutral atoms type systems. So what I've done here is I have positioned 6 atoms in a square lattice structure. So with equal distances of, I think it's still 8 micrometers. With these 6 atoms, again, as an illustration, each atom corresponds to a node in my graph, and there is a visualization of an edge, of a connection between the nodes whenever they are sufficiently close together, in this case, within a certain threshold for the Rydberg blockade radius. So we have this nice graph representation of our atomic register. And this experiment, initially designed as what we call the antiferrometric state experiment, is nothing else but an Ising type Hamiltonian's implementation in 3 separate steps. What I wanted to illustrate is that we can talk about this problem from a very, very different perspective. So for a second, let us forget all the physical components that go into this and really look at it as a mathematical structure only. So it is a graph representation. We have a collection of 6 nodes and we have edges drawn between certain of these nodes. As I mentioned in the beginning, there are various different problems that we can consider for a graph structures, and one of them that's going to be the key element is finding a maximum independent set. So finding independent sets in a graph, trying to select nodes that are pairwise disconnected. So if I look at the execution and follow what's happening, what I will notice is that the solution itself will converge towards two quantum states. In particular, as you can see in this representation, at the end of the execution, I only have two potential solution candidates. And interestingly enough, one of the two solution candidates selects the nodes alternatively. And we have seen from a physics perspective how that came about. But if we think about it from a graph optimization point of view, what we can see here is that the solution highlights three nodes, and each of these three nodes, pairwise, these three nodes are not connected. So what it has done is selecting an independent set. Looking at the other solution, it selects the other three in an alternating fashion, again, giving rise to an independent set, which in this case coincides with the maximum independent set solution. So in this 6-node graph, I can select up to 3 nodes in a way that there is no two of these three that are connected. So interestingly enough, this has provided a solution to the maximum independent set, even though I was solving a completely different problem. Or was it completely different? So if you think back on what's happening from a physics perspective, the experiment itself, what it's doing, it's sending the laser signal to the whole system. So in a sense, it's starting to excite the whole atomic register. So all the atoms are receiving sufficient energy to enter into the high energy Rydberg state. However, atoms that are neighbors, so atoms that are connected, they are within each other's Rydberg blockade radius, meaning that if two of these atoms try to get excited, try to reach this Rydberg hyperexcited state at the same time, one of the two would need to be pushed to a lower energy rate. So they cannot both occupy this high energy state if they are this close to each other. This is the Rydberg blockade phenomena, which implies that one of the two atoms needs to be pushed on a lower energy level. So let's think about what can happen if you look at Q3 and Q4. If, for instance, Q3 manages to keep its high energy state, then Q4 needs to be pushed to a low energy state. Similarly, between Q0 and Q3, if Q3 managed to keep its high energy state, then Q0 was pushed in a low energy state. If Q0 and Q4 were pushed to a low energy state, that means that Q1 can reach its high energy state, which will in turn imply that Q2 has to be in a low energy state. So Q4 and Q2 were in a low energy state, so Q5 can reach a high energy state. This corresponds to one of the two solution candidates. So intuitively, by performing a similar experiment, I am able to select nodes that cannot be connected with each other. So I am leveraging the fact that whenever there is an edge drawn in the graph representation, there is a physical connection, meaning that the Rydberg blockade phenomenon can happen, so that not both atoms can become excited at the same time. This implies that there is a natural selection in between the atoms on who can reach a high energy state and who can reach a low energy state. I'm leveraging this fact to provide a sort of initial selection of what becomes an independent set for my problem. Let's talk a little bit more about how this selection procedure is happening. For this, we need to understand how we interact with the quantum register itself. So as I mentioned, the algorithmic implementation has two components. First, positioning the atoms, so creating the atomic register inside the neutral atom system. And second, designing the pulse, the laser pulse that interacts with this system. So back on Wednesday, I mentioned that when we are parameterizing the laser system, we have access to two main parameters, the amplitude, here in this formulation, that's the omega, and the detuning parameter, which is the delta. The whole Hamiltonian, the whole driver Hamiltonian that's acting on our system has two, or in this sense, three main components. There are the one-body terms. So these are the parts of the Hamiltonian that come from the external field. So as we have seen in this representation, when we talk about the Hamiltonian, there are two-body interaction terms and a one-body interaction term with an external field. So in this Hamiltonian representation, the two first terms correspond to interaction with the external field. In this case, our external field is the laser pulse we are shining on the atomic register, and the two-body interaction terms that are entirely a function of the geometry itself. So as you can see here, the Hamiltonian operator has a term that's entirely dictated by the geometry itself. So placing the atoms has an impact on how the Hamiltonian is shaped, how our operator looks like. That's why it's very, very important to find good locations for the atoms themselves, because this second part is entirely controlled by the geometry itself. The first part, however, is controlled by the laser pulses themselves. For the laser pulses, as I mentioned, for the amplitude, you need to think of it as a source term, so with a positive index in the Hamiltonian. The detuning parameter is the sinc term. It's with a negative coefficient. So that's the main distinction, that the two parameters that evolve over time, one impacts the system variable with a positive coefficient, the other one with a negative coefficient. So in a sense, the amplitude parameter is adding energy to the system. The detuning parameter is subtracting energy from the system in a continuous in time fashion. So are there any questions so far? Yeah, so what kind of problems can be modeled with a QUBO type problem? So QUBO stands for quadratic unconstrained binary optimization problems. So each of the words implies a specific restriction. So quadratic means that we can go up to second order terms. For a lot of the problems that we are dealing with on an everyday basis, the cost function has linear and second order terms only, but there are some limitations. So equivalent to QUBO, there is another problem category called HUBO with an H. So it's higher order unconstrained binary optimization problems. So in case your cost function contains terms that require multiplying 3 variables, 4 variables, etc., these can correspond to these what we call higher order optimization problems. They can be approximated by quadratic optimization problems, but that will be an approximation, not an exact solution. Typically, depending on the parity of the largest order term, you can introduce some kind of reduction to lower order terms. That's quite efficient. So quadratic optimization problems can be a powerful tool in handling, for instance, fourth order, sixth order, and pair or order terms. However, with odd orders, they can have much more difficulty for approximation. With that said, there is really, I would say, a small subclass of problems that fall into higher order optimization problems. but this can happen, and in this case, quadratic is not sufficient. The main limitations of a QBO type representation, however, are the other two letters. So the U that stands for unconstrained and the B that stands for binary. So typically, problems that come from a real life are rarely binary problems. Binary variables arise when there is an indicator involved. So whenever the problem formulation, in a sense, is a bit more artificial, but for a lot of the actual optimization problems, that's not directly the case. However, what's good is that integer-based problem formulations can be connected to binary variables with various different strategies. The main limitation of the QBO type problems is the unconstrained part, because it's quite rare that you have to solve an optimization problem that has no constraints. Typically, because without constraints, a lot of the problems can become relatively simple. But in practice, it's because there is always some limitations, some constraints present in the problem formulation. So a QBO is not all-encompassing. It's used as a first step in complexifying problems. So moving towards something that's easy to solve, which is the linear programming that we have seen in the beginning, to something that's much more realistic. So the next step from a QBO would be to relax, to remove one of the letters, to move for much more realistic optimization problems. So when we talk about simulated annealing or annealing in general, we typically refer to adiabatic type processes, so that involve slow evolution over time to move the ground state of a system to a target state of a potentially excited system. So this is a key strategy to solving various different problems, not only in quantum simulation tasks, but also in optimization. If you design your system well enough, your evolution is sufficiently slow and well targeted, you can reach various different quantum states that, if you design the experiment correctly, will represent the solution of the target problem. We will see a couple of examples in next week's more advanced session, because that requires a bit more discussion on the operator side. Is entanglement explainable by graph theory? That's an interesting question. I would say depends on where your graph came from, in a sense. So if you look back on for a neutral atom system, graphs represent the atomic register, so the position of the atoms, as well as the physical connection between the atoms. Since for a neutral atom system, entanglement is inherently related to the physical connection between atoms. So you can only entangle atoms or the energy states of atoms if they are within the Rydberg blockade radius. In this sense, this graph representation with the edges gives you an indication on the what I would call entangleability. So the fact that you can entangle certain atoms and the edges model which atoms can become entangled. However, it's not a direct, I would say, indicator, meaning that if there is an edge, that does not necessarily mean that the atoms are entangled. Sorry, if anything, I would say that the edge in this graph representation indicates that the nodes, so the atoms corresponding to the nodes, can become entangled. So you can think of it in that way, that a capability to become entangled can be modeled by the graph. This, however, is not only limited to neutral atom systems. So if you think of a superconducting quantum computer's microchip architecture, the microchip architecture can also be modeled by a graph structure in which each node is a qubit, a superconducting qubit, and you draw edges between neighboring qubits that are physically placed next to each other. That typically gives rise to a square lattice-based graph representation of the superconducting chips architecture. And in this case as well, the edges, so that physically depict neighbors, mean that you can entangle directly those two qubits. But once again, in this case, the graph representation indicates which atoms, which qubits can become entangled, and it's not an indicator of who is actually entangled. That would require a bit more dynamic representation. Yeah. So why have we chosen this kind of pulse for the antiferrometric state experiment? So yes, there is a reason for choosing this pulse in particular. So if I execute this method, what I can see is that during this the evolution process, at the end, I reach two solution states, two pure solution states. So there are no additional quantum states that can appear. This is typically an indication that the experiment has been well designed to really solve the particular type of problem you want to solve. So the idea behind these three pulse sequences is an adiabatic evolution. Adiabatic evolution requires for you essentially three main things. The first thing is that the amplitude parameter needs to start from 0. So you will turn the amplitude up, turn the source term up, and it needs to end in 0. So then it needs to be attenuated at the end. The amplitude parameter should stay either positive or negative. So it should not change signs. And the detuning parameter should change signs. So these are, in a sense, three practical constraints in designing the experiment. Other than that, you are free to experiment with various different forms. So as we have seen in one of the examples, so let me load up one of the demo sequences we have seen. Yeah, let's stay with this. We have seen on Wednesday. So in this case, for our atomic register with the 6 nodes in a square lattice, I've designed a single pulse. Again, as you can see, it's in a sense respecting the same constraints. I will make a quick modification just to correspond to exactly what we are doing. Okay. Let's put it. Yeah. So again, as I mentioned, for an adiabatic evolution, what we require is to start off from 0, the amplitude parameter, do not change sign, and reach 0 back again. So there is a ramp-up phase. There is what we call a mixing phase, so interaction phase, and there is an attenuation phase. For the detuning, technically what we require is to have a shift, have a change in sign, to shift from a pure source to from a pure sink to a sink-based source. And if I execute this algorithm in particular, what I will see is that a similar type of process is starting to take place. However, the solution itself is much more polluted. So the experiment itself, again, what it does, it selects nodes that are sufficiently far away. which is a good thing. So it does not really select nodes that are connected. However, it fails to capture the two main solutions and the two main targets because it was, I would say, arbitrarily selected as a first guess. In particular, in this scenario, so the three main steps, the ramp up, the mixing part, and the attenuation have a very, very specific role. So if I launch the experiment and stop at the strategic position, the ramp up introduces the intensity of the laser pulse, meaning that it starts to excite each of the individual atoms. So here is the advantage of working with an emulator. This is something you could not do with quantum computers because you cannot just stop the experiment halfway through and then continue. But with emulators, we have solved the system directly from a numerical solver, so I can do that. So the ramp up introduces the laser pulse to start exciting all the atoms. Then with a continued laser pulse, but shifting the sync term from a negative sign to a positive sign, it starts introducing the entanglement effect. So the atoms have received sufficient energy at this stage to reach the high energy state. However, they cannot both enter into the entangled state. So one of them is being pushed to a low energy regime. Therefore, by the end of this interaction phase, where we maintain, in this case, the same amplitude, so the source stays the same, the sync term is being alternated to make the interaction, the entanglement part more efficient. By the end of it, I see that we have two key solutions that arise. And herein comes the third phase that's just as important, the attenuation to relax, to stabilize the system. And through this stabilization, the other quantum states that were still present, these other errant states, slowly die out, disappear from the solution space by the end. So these three components, in a sense, are artificial. So they have been designed, so the exact values, the exact parameters have been computed in order to provide for an exact solution that only gives these two solution candidates for you. This is designed specifically for this geometry. So for this square lattice with 6 nodes with these atomic distances in mind. So this is something, this is a computation that you can carry out by knowing the positions of the atoms. You can exactly determine the two-body interaction terms in the Hamiltonian. For an Ising type system, then you can calculate with these approximations. So I want a linear ramp up, I want a constant amplitude, and I want a linear ramp down. You can calculate exactly what are the parameters you should put in to instill a perfect evolution. This can be computed because you are working in a square lattice, so with good coordinates. If you were to perturb the geometry, so if I were to move around the atoms a little bit, as I can see, there is higher likelihood of having still the good solution, but there is also an errant state that appears here. So I've moved around the geometry, therefore the solution, the exact pulse I've designed that worked perfectly for the initial geometry will no longer work as intended. So this sequence is really designed to work perfectly for this particular geometry. This is something that you can physically calculate to determine the exact parameters you would need. But the main idea, the generic idea, is that you need to follow some of the principles of this adiabatic slow evolution, which has this ramp-up phase, the mixing phase to keep up the excitation, to excite the whole system to allow for this natural selection, and then the ramp-down phase to try to stabilize the system. So let's move on to the next part. So as I mentioned in the beginning, a particular focus is on studying the maximum independent set problem. And for that, we need to specify exactly what is a maximum independent set problem, because the nomenclature can be a bit confusing. So to illustrate it, I have prepared a very, very simple example to go through the various different definitions that can arise in this context. So the first definition is the definition of an independent set. So an independent set is a collection of nodes that are pairwise disconnected. So there is no edge running in between any two nodes in the independent set selection. So if we consider this simplified graph with 6 nodes in total, as we can see, if we were to select these two nodes on the left, there is an edge in between them, so it's not an independent set selection because that forbids us from having edges between the selected nodes. However, if we were to select the one on the middle on the bottom, these two nodes, so one on the left and one on the right, there is no edge running in between them, so they correspond to an independent set selection. Then comes the more complicated part of it, because we have technically two different or two connected but not exactly the same definitions. So there is maximal independent set and maximum independent set. So what's the difference between the two? So a maximal independent set refers to an independent set to which you can no longer add nodes to keep it independent. To illustrate this, so there is the example on the top right part. You have two nodes selected, one in the left on the middle and one on the right in the middle. There is no edge running in between them, so it's an independent set. And if I were to add any of the other nodes to the selection, so the one on the bottom, if I add that, there is an edge that appears, so it's not an independent set anymore. If I add the top left one, there is an edge that appears, so it's not an independent set, etc., etc. So to this set, so to this selection, I can no longer add more nodes to keep it independent. Therefore, it's a maximal independent set, referring to the fact that I can no longer extend it. On the contrary, a maximum independent set refers to an independent set selection that has the largest number of nodes possible for the selection. An example for this is in the bottom right section of the screen. So we have 3 nodes and pairwise, there is no edge running in between the 3 nodes. So it's an independent set. And in this graph, we cannot select a collection of 4 nodes such that they are pairwise disconnected. This example illustrates quite well the subtlety, but still the difference between a maximal independent set and a maximum independent set. This typically implies that progressively generated or brute force type greedy algorithm can lead to suboptimal solutions because depending on how you start creating your independent set, you can end up with an independent set selection that can no longer be extended. However, it could not be actually an optimal selection. So these two examples illustrates, in a sense, what's the difference between maximal and maximum. In practice or in reality, the distinction is more for a mathematics perspective than anything. So the important part is still the independent set selection procedure, but this distinction between maximum and maximal will play an important role in the algorithmic design itself. So as we have discussed, neutral atom systems are particularly good at encoding graph structures, And due to the fact that the physical experimental design relies on sending energy, sending the laser pulses to the system to excite it, and excitation can only happen, or interaction can only happen on a distance-based relation. So whenever you have edges between the nodes, this implies that with a well-designed experiment, this laser-based interaction can instill an independent set selection for a problem. So this independent set selection requires, as I mentioned, an adiabatic type evolution. So we have seen something similar as an initial example. Again, for an adiabatic evolution, the key is a slow evolution that increases the amplitude of the source term progressively, keeps it in a same sign, and then decrease it progressively. So ramp up, mixing, ramp down. These are the three main phases. In actuality, what is happening is that from this initial known state, where everyone is in their ground state, you are slowly increasing the energy, and as we know, physical systems tend to keep in their own ground state and their minimal energy state. So if you slowly vary the system itself progressively, you can keep it in its lowest energy state. And by the end of the experiment, you can reach a target Hamiltonian, which hopefully solves the problem, the problem that you were interested in. With that said, an important distinction is to be made is that actually this adiabatic evolution selects large independent sets. We have seen, if you go back to the examples on Wednesday, that the same sequence always favored, in a sense, an alternating selection, but it did not necessarily give back the maximum in terms of size. If I go back to my initial simplified example and execute the experiment once again, what I can see by the end of the experiment is that there were quite a lot of proposed solutions with high probability. What I can see is that, for instance, if we look at this selection for this 6-node graph, the two opposing nodes have been selected. This corresponds to a maximal independent set because you can no longer add nodes to this selection to keep it independent. No matter what other node you would add, there would be an edge that is formed, so it would no longer be independent. This is similarly, it's not the case here because you can extend it. It is just a partial solution, but it is the case for this solution as well. And as you can see, this and this as well arise with a rather high probability comparatively to the other solution candidates. So depending on the precision of the experiment, this adiabatic evolution favors giving back large independent sets. It might not be a maximal because you could potentially extend it. And it most certainly might not be the maximum independent set, so the largest possible that you could select. Herein lies the importance in optimizing your algorithm, optimizing the laser pulse, in a sense that you are able to favor the actual maximum as opposed to other potentially errant states. Nevertheless, it is still useful to have such a selection because depending on the type of algorithm you are designing, being able to select independent sets on a graph itself can be a very, very important subroutine. So it's a subtask that needs to be solved by the algorithm itself. More or less, an additional feature of this selection is that it's quite robust in presence of noise. So if the system is still noisy, the selections will still take place because it favors the physical interactivity. So the independence criteria will rarely be actually broken by the solutions it will propose. I say rarely because depending on the selection, you can still find yourselves with some conflicting answers, but 98% of the cases, the selection will still come back to an independent set selection. And noise resilience makes it very, very NISC, so noisy intermediate scale quantum compatible algorithmic routine as well. So why the distinction between selecting maximum independent sets for an optimal implementation or not so optimal implementation, selecting just independent sets? We will come back to that in a second when we discuss how you can use this maximum independent set solver or independent set solver as part of other algorithmic implementations. Before that, I wanted to allude to a couple other constraints. So if you remember, the graph representation of the atomic register is geometry-based, and the geometry is constrained by the distance between the atoms themselves. So we can only draw edges whenever the nodes are sufficiently close to each other. However, we need to draw all the edges that represent connection between nodes that are sufficiently close together. So this gives rise to what we call a unit disk graph, which is a specific subclass of graphs. As I mentioned, not all graphs can be represented this way. However, there are certain techniques that allow you to reformulate graphs by representing them in a unit disk fashion. So one such example is this graph here. So it's a very, very simple graph with 5 nodes in total, and it is actually a non-unit disk graph, one of the smallest potentially examples of a non-unit disk graphs, meaning that you cannot position the nodes on the Cartesian plane such that edges are drawn only if the nodes are sufficiently close together. Typically, what would end up happening is the nodes 1, 2, and 3 in the middle layer would need to be sufficiently close together to have an edge between them, but you cannot have an edge between them from the graph point of view. However, you can design a layout, you can design a positioning of the atoms with extra nodes and edges to turn this graph into a larger but unit disk graph. So this can happen still on a two-dimensional plane, but depending on graph structure, in some cases you might need to step out of the space and use three-dimensional structures. This naturally incurs some limitations on which graphs can be efficiently represented and implemented on a quantum device itself. Nevertheless, it's worth knowing that although the direct encoding is limited to unit disk graphs, there are techniques that allow you to have non-unit disk graphs being represented as unit disk graphs as well. As I mentioned before, it's important to keep in mind this independent set selector, not just as a solution strategy in itself, but as an algorithmic component. The reason for this can be visually very, very simply illustrated if we go back to one of our other problem types that I presented in the beginning, which relies on graph coloring. So in particular, the vertex coloring problem or minimal vertex coloring problem. So as a reminder, in the minimal vertex coloring problem, we are tasked with associating colors, labels to the different nodes, such that two adjacent, so two nodes that have an edge in between them, do not have the same label, they do not have the same color. And why it's a minimal vertex coloring problem, it's because we want to use the least amount of colors, the least amount of labels possible. Because a trivial solution to the vertex coloring problem would be to allocate a different color for each of the nodes. This would obviously satisfy the constraint that if there is an edge, the nodes connected by the edge cannot have the same color. If you use different colors for each of the nodes, obviously this is satisfied. However, that's why the minimal vertex coloring exists, is to keep the number of colors used as low as possible. And this is what makes the problem actually complicated, because if you add one extra node, that will imply adding a couple of extra edges, but that will imply having multiple new checks to try to find if coloring can be extended or if coloring can be revisited to be applied for this new larger graph. So as you increase the size of the graph, it increases exponentially the amount of potential coloring or the number of potential colorings to be tested. For this reason, solving it exactly typically is not a viable strategy. In practice, people use heuristic or approximative algorithms, different search methods that are able to find good colorings and in certain scenarios are able to also guarantee an optimal coloring as well. So to give you a bit more visual context for the graph coloring problem, as I mentioned, the objective is to allocate colors to the nodes of the graph such that pairwise the no two colors are allocated to let's start it again. So to allocate colors such that connected nodes do not have the same color. Here for this 5-node graph, the selection a good coloring is provided on the right-hand side. This is not the only potential coloring, but the advantage here is that it only uses the least amount of colors possible, which is 3 in this case. Why graph coloring in particular is important. So here is a little bit of a teaser for next week's session on a deep dive where we will discuss the particularities of this method. But in actuality, it can be used to solve various hard combinatorial problems on graph-based structures, one of them being an example arising from telecommunications scenario in which you have graphs because you have networks naturally present and problems that you can tackle rely around building up on an existing or a future telecommunications network, for instance, a collection of antennas, or in this case, what we call telecommunication cells, and allocating frequencies or identifiers to these cells by respecting certain constraints. And the constraints that manifest in this problem formulation can be associated with the coloring of the associated graph. But we will discuss more on that a little bit later. Another type of representation is surprisingly portfolio optimization. Portfolio optimization can also be tackled by graph representations. So portfolio optimization typically is formulated as optimization problem, purely mathematical optimization problem. However, you can introduce graphs in this scenario by creating what we call market graphs. So allocating assets to nodes and then drawing edges, drawing connections to nodes whenever there is correlation or anti-correlation in between the assets. In this sense, the portfolio optimization problem can be viewed as what we call a maximum click selection problem. So trying to find the largest fully connected set, or equivalently, it can boil down to finding a maximum independent set on the complementary graph. So even for this seemingly abstract representation, the maximum independent set problem can play an important role. And even more interestingly, one of my preferred examples from optimization problems is bin packing or a knapsack problem. So the bin packing or the knapsack problem relies on the fact that you are tasked with filling up a container, your knapsack, your bin, with specific objects. So these objects have a specific weight and a value. The objective is to fill up your backpack up until the limit in terms of weight, such that the value of the object is the maximum. So this can be formulated as with equations and variables as a purely mathematical optimization problem, but this can also be represented by a graph-based problem by the intermediary of what we call a constraint graph. So a constraint graph is a very, very important artificial graph structure that allows you to model non-graph problems as graph problems. The key idea here is that the objects you want to place will become the nodes, the vertices of the graph, and you will draw edges whenever there is some kind of conflict between the two objects, between the two nodes. For instance, in this scenario, the conflict can be in such a nature that you cannot place both of the objects in the bin at the same time. But the conflict itself can have a rather large definition. This gives you a lot of flexibility in trying to model with graph structures. With this with this graph representation, with this conflict graph or constraint graph representation, selecting the optimal solution, so selecting the optimal placement of the objects boils down to selecting a maximum weighted independent set of this constraint graph. So maximum independent set really arises in various different scenarios. In the bin packing problem for a more abstract representation on constraint graphs, for portfolio optimization, or for graph coloring type problems as well. So as a last example for today's session, I wanted to come back to the graph coloring to illustrate the connection between graph coloring and independent set selection. So as I mentioned, the task here is to color the nodes such that no two neighboring nodes have the same color. So this is reminiscent of the definition of an independent set, because an independent set selection corresponds to nodes that do not have edges in between them. Therefore, naturally, you could think that if I am able to select an independent set, a large independent set, potentially, then I can color all the nodes in an independent set with the same color. And it is indeed one of the potential subtasks you can perform. So finding independent sets in a graph can give you a good idea how to start coloring the graph in an optimal session. Of course, there is no guarantee immediately that just looking for independent sets can lead to an optimal coloring. However, it is an important subtask, an important component that can be leveraged to build an actual method for an efficient coloring technique. And we are going to deep dive into this technique next week's session on Wednesday, when we will focus on not only graph coloring and its implementation, but the aforementioned telecommunications example in much, much more detail. With that said, I have reached the end of what I wanted to share with you on the optimization section for neutral atom systems. So if there are any more questions, please feel free to ask. So yeah, there was one more question with the Pasqal Studio showcase, I think, when we discussed how to create the adiabatic pulse to solve that particular problem. So can we calculate the perfect pulse? Or can we always calculate the perfect pulse? The answer is no. So you can, it really is a function of the geometry. So typically for structured layouts like square lattices or triangular lattices, this is something that you can solve analytically. So you can exactly determine what's the optimal pulse. However, for much more complex geometries, the problem becomes increasingly more complex, and in a lot of cases, the solution is not even analytical. However, the idea here is that you have a lot of flexibility. So here I have chosen to apply a single pulse with this shape. Here, for the exact solution for the structure grid, I needed 3 separate pulses, one after the other. If you have more complex geometries or larger number of nodes, what you can potentially leverage is the additional feature of you having total control of how this pulse actually looks like. So herein, let me just quickly create a larger selection. When you design a pulse, you have different choices. And one of them is the very, very robust interpolated method. So for interpolation, you can create as many connections as you want, which allows you to try to approximate or try to compute exactly the adiabatic shape you would need. Depending on the complexity of the geometry, you can make very, very good approximations, or in some cases, you can even find an exact shape. But here, the idea is that you have access to composing pulses one after the other by linear segments, but you can also have access to interpolation to design much more complex pulse shapes depending on what you would need. With these 2 tools at their disposal, the parameter space you can leverage to design this experiment is quite large. So you can leverage it to design efficient approximations or in some cases even find the exact solution. But the answer is no, in general, the optimal pulse that provides the perfect solution is rarely such a simple task, or in a lot of cases, you cannot even determine it. However, with a good enough shape design, pulse shape design, you can get almost arbitrarily close to the perfect solution. So how do you truncate the interaction range and set the threshold of connection between 2 distant atoms? So this is something that on the real machine is dictated by the physics, because the interaction range is related to the Rydberg blockade phenomena, so which has a cutoff point depending on the exact definition of your hyperexcited state. So if you remember, we discussed that we encode quantum information in the energy state of the atoms. 0 information is the reference state 0, I should say, is the ground state, and reference state 1 is the hyperexcited Rydberg state. Depending on the machine, this hyperexcited Rydberg state can be on the 60th orbital, can be on the 70th orbital, meaning that orbitals above this, so distance ranges above this, are unreachable by the atomic register or by the excitation states. So that is what dictates what the cutoff point should be. So from a physical perspective, it's the machine setup that dictates what's the interaction range. So it is something that should be given. From an implementation or algorithmic perspective or programming perspective, I should say, since you have access to virtual devices of your own design, you can play around with the parameter yourself. But this is typically not something that you as a developer would choose. It is something that is constrained within the parameterization of the quantum processing unit. So using quantum bits, is it impossible to connect same graph color at the same time? I'm not sure I understand the question, what you mean by same graph color, connecting same graph color at the same time. Sorry. If you can precise the question, I'm happy to answer it. Yes, so to design a control Z, so moving from 3 atoms to a 4-atom system, you need to incorporate a bit more ingenuity in the design, because as you remarked correctly, you cannot really make 4 nodes equidistant. So the layout needs to be a little bit different. So I showcased the CZ and CCZ, in which case distance did not play a major role, but to add an extra controller, there are, I would say, 2 ways to go about it. There is the preferred way of decomposing the 4-way gate, so the control Z into lower gates, a sequence of lower gates. Instead, to some extent, the other way is to fine-tune the interaction shape to counteract the fact that opposing nodes in your square-shaped or rhomboid-shaped quantum register, the opposing nodes have a stronger interaction coefficient with each other. So what I mean by that, let me quickly destroy this experiment and move the atoms a bit closer. So typically for a CCZ in architecture, you would naturally end up with a consideration of 4 nodes. And here the issue is that the diagonal nodes are further away than the nodes on the actual edges of the square, meaning that when you create the entanglement and the interaction, typically if one of the target is here, you need to choose different coefficients for the diagonal one than for the 2 side ones, because the distance, so the interaction strength itself is not the same. So to ensure an equivalent control, the parameters need to be chosen appropriately. So this will give rise to more of an asymmetric structure that you need to play around a little bit with the local channels to reproduce it. So the answer is you cannot make the same distance. That's how geometry works in the 2-dimensional space. However, you can counteract with creating an asymmetric structure for the laser pulse definition. This is a very interesting question. So can we solve such problem or similar problems by means of machine learning? This is a very, very fair point, and this is something that I wanted to introduce in the more advanced session, because I was unsure how everyone is doing with machine learning. But yes, indeed, machine learning is a very, very powerful tool that can be leveraged in the neutral atom system, particularly because you have a lot of degrees of freedom, a lot of flexibility to try to find efficient register designs and to try to find efficient parameterizations. So both the geometry, the layout, and the pulse shaping can leverage machine learning tools to provide good guesses to have these models trained to provide good configurations. So yes, machine learning has a powerful role to play to help with the development. And on the second part, so your thought is indeed correct. And not just with machine learning, but in general, so algorithmic development for adiabatic evolution, so for optimization type problems as well, happens in a similar fashion, is that you are testing, you are optimizing for a smaller set, so simpler problems, and then you will be executing it on the actual device for harder problems, wherever the emulation, either local or cloud-based emulation, no longer provides enough computational resources. But what you have described is indeed a typical work cycle. So you want to design smaller experiments in order to play around and fine-tune the shape, and then you want to scale up your experiment based on your initial findings. So the inherent problem when you're doing vertex coloring is indeed to find an optimal labelization, if you wish, so that no two neighboring edges have the same color. So that's the fundamental rule of the vertex coloring problem, and that needs to be respected. With that said, so from a quantum state perspective, if you were to model your graph nodes as quantum bits, since information works differently with superposition, you can create abstract graph structures and that no longer are represented by graphs in a traditional sense, and then therefore can accommodate what you're asking for. But there, so connecting same colors or redefining the problem itself, it sort of steps out of what we traditionally consider as graphs. So you would enter into a regime of multigraphs or other types of much more complex mathematical structures. But yes, there is indeed an extended amount of theory behind how quantum and graph theory can be connected on a more abstract layer. So can we solve the coloring problem by solving many MIS problems? Yes, indeed. That's what I was alluding to. And that's going to be one of our solution strategies that we'll detail next week. And also do some implementations on that. Indeed, so the maximum independent set problem or independent set search problem in general and the vertex coloring, the minimal vertex coloring especially, are inherently related. Because as I mentioned, if you select an independent set in your graph, then you can color all the elements of the independent set with the same color, because they do not break the rule that you cannot connect the same colored nodes with an edge, or there cannot be an edge between nodes connected by an edge. It cannot be an edge between nodes colored by the same color, sorry. So being able to select independent sets provides you an initial way to tackle coloring. Therefore, selecting maximum independent sets can lead you to close to optimal selection of nodes for the different colors. However, I have to say that it is naively only close to optimal, because guaranteeing an optimal coloring, guaranteeing that you cannot use fewer colors to do the coloring itself, is a bit more complicated, but it's still one of the key components. So selecting large independent sets and coloring them with the same color, and then making new selections for new colors is indeed a good way to start designing an efficient algorithm.